Welcome back everyone. So we are discussing about the X-ray spectrum, continuous X-ray spectrum and characteristic X-ray spectrum. So we discussed that there will be 4 transition which actually correspond to the emission of the X-ray photon, that are L2K, M2K, N2L or M2L. 4 transition will be there. So now we know that this energy gap L2K, this is energy gap is higher. So if energy gap is higher, then obviously the lambda, if the energy gap is higher, then lambda will be less. These things are there. Okay, so let us understand one thing. Here there will be 4 photons, k alpha and k beta we can see, but there will be also L alpha and L beta, as I discussed in the last part. Okay, so let me write it: k alpha, k beta, L alpha, L beta. But L alpha, L beta, actually these peaks less intensity. Okay, and k alpha is this and k beta is this. So this is our characteristic spectrum, and but most importantly this k alpha, because the intensity of this k alpha is higher. K beta we can neglect. So both all 4, k alpha, k beta, L alpha, L beta, this depends upon the energy levels, because this depends on the energy gaps, and energy gaps essentially depends on the energy levels, and energy levels is totally depends on the characteristic of that atom only, because it depends on Z. Z is the atomic number, we know that, but in that time that was not known, because it's actually the before the Bohr's atomic model. But that depends on the metal, that depends on the atom we can say, or because this is the metal, so we can also call it depends on the metal character. So now what Moseley did, very importantly, now we will study the Moseley's law. Okay, so Moseley's law, Moseley, he actually analyzed the results. He then analyzing the result, he make a plot which essentially gives some fundamental character of that atom or that metal, you can say. What is that? We'll identify that, but before that we'll look at the graph that obtained by Moseley. Moseley actually plot root over nu. Okay, what is the root over nu? I will come into that. And in this way, in this x axis, he plot the elements of periodic table. We know in that time Mendeleev gave the periodic table. There was the old periodic table given by Mendeleev, and in that periodic table the elements were organized in terms of their atomic weight, and in the same group in periodic table what's happened. Let me just give a small recap of periodic table. Mendeleev periodic table, not the modern periodic table, not the longer one, because in that time that was not known. In Mendeleev periodic table, in the group, the main idea was in groups, let's say in this group these elements are there, then the property of these elements will be similar. So this is actually a tabular form where the elements in the same column have the same properties. This is the, and these tables was made by the Mendeleev, and this was organized in terms of atomic weight. But there are some flaws, we will come into that. That was resolved, some part of that was resolved by this Moseley's experiment, Moseley's law. So what Moseley did, that Moseley plot this del nu of elements, and he observed a straight line like this: aluminum, silicon, chromium, not chromium, it is actually chlorine, potassium, calcium, titanium, and so on. And here we can see these are actually lanthanides, molybdenum, neodymium, these things are there, rubidium. So this was the results of Moseley. You can see there is a straight line he obtained. What is the del nu? Del nu is the corresponding frequency of that k alpha peak. There are 4 peaks, so k alpha peak is there. So that peak, k alpha peak, this k alpha peak obtained for a certain wavelength, so we can convert wavelength into frequency. How? Just we have to take care about this formula. So if you then we can, okay, if you divided C by that k lambda, or means the lambda of that k alpha peak, then you can obtain the nu, which is actually, we can write it k nu or k alpha nu more prominently, k alpha nu. So this nu actually k alpha nu, and we have taken the root, not we have, the Moseley taken the root and he obtained this nature. So this was the result, and this result was actually analyzed, or we can say actually explained by the Rutherford in 1920. I think, what was the, yes, this result was obtained by Moseley at 1913 by Moseley. Moseley was obtained this result, and 1920 Rutherford explained this Moseley's curve, Moseley's plot, we can say. So this was explained by Rutherford. Okay, so what was the logic, what was the explanation given by the Rutherford? Okay, let me write it, then we will explain. So Rutherford said that there was a fundamental quantity of metal or atom, we can say, which increase by regular step. This is some regular step, so that is increasing, right? That is increasing. So that is increasing. So that fundamental property, fundamental quantity, that is increasing by regular step as we pass from one metal to another metal, or we can say one element to another element. That is not only for the metal, for other elements as well. So that was the statement given by the Rutherford, and he solved. He identified that that quantity actually depends on that nu actually depends on that quantity, that is actually the Z. What is Z? Z is actually atomic number. That means when you pass from one element to another element, Z is increasing, and while Z is increasing, and corresponding peak, k alpha peak, frequency of the k alpha peak also increase, but there is a relation between that k alpha frequency of the k alpha peak and that Z, and that is that root nu is actually proportional to the Z. Z is the atomic number. So what was the statement? Moseley's law, that, let me write, very important, statement of Moseley's law. Okay, different color. The square root of the frequency of a peak of the characteristics X-ray spectrum of any element is directly proportional to the atomic number, square proportional to the atomic number, yes, of that element. Okay, means what I have said, that root over nu proportional to Z. Okay, so this is the Moseley's law. The square root of the frequency of a peak of that characteristic X-ray spectrum of any element, that can be molybdenum, that can be silicon, titanium, anything. So that is actually directly proportional to the atomic number of that element. So root over nu is actually proportional to the Z. Z is the atomic number. But we have to explain. We know Bohr's model for the atomic structure. So on the behalf of that knowledge, we want to explain this result. So let's start. Now we want to explanation of Moseley's plot from Bohr's theory or Bohr's atomic model. So, this is our next target. Okay. So, if you remember what was the Bohr's atomic model? Bohr's atomic model, let me write it, draw it. Okay. So, there are all other levels as well, but we are interested only KLM, and let me write, draw one more. This is N. Okay. According to Bohr's atomic model, what was the energy of electron? Energy of electron is, let me write, that is En, which is minus RCH by n square, where R is the, these things already discussed, Rydberg's constant. Okay. And for hydrogen atom, okay, one thing we have to keep in mind always, this Bohr's theory is for only hydrogen like atom, not for any atom, because for any atom there are more than one electron, and we have to account also the electron repulsion term, that we did not account while calculating the energy, these things using the Bohr's model, but that is not trivial. Even today, till today, scientists can only deal with the hydrogen like atom problem. If you look at the quantum mechanics as well, hydrogen like atom problem can be solved, but that is also very difficult to solve. But still we can solve hydrogen like atom problem, but in case of more than one electron is there, if there is one more than electron, if it is helium even, then also we can't solve that problem. So that orbital, we know that ASP, these orbitals also for hydrogen atom, only for hydrogen atom. For helium, lithium, these atoms we don't know how it looks like, but we can approximate. That is the different thing, but we have to keep in mind that this Bohr's model is also for the hydrogen like atom. Now for specifically for hydrogen atom, this will be n square electron volt, or for any atom it is actually, this is for hydrogen, for any atom it is this. So this is our formula, we know. So you can say we can directly apply this, because we have to ultimately find out the k alpha, right, this peak, this k alpha. That means we have to subtract the energy, this EL minus EK, and that we have to convert in the frequency, that should be proportional to the Z, root Z, sorry, Z should be, that root over nu should be proportional to the Z, but that is not the case, because first of all we are not dealing with hydrogen atom. So there are other electrons are also there, so we have to keep in mind that. Still we can approximate it to the hydrogen like atom, and then we can give some argument to solve it. But also there is another one thing, because in now one electron is also there in the k orbit. Let me explain. So we are now focusing on the k alpha peak, k alpha. This peak is actually due to the transition of the electron. If the one electron is kicked out from the k orbit by the cathode ray electron, then to fill up that vacant position, electron from the higher orbit jump to that k level, k orbit, and due to that de-excitation, the energy released, the photon of corresponding energy is released, and that is the reason behind the k alpha peak in the X spectrum. Okay, so we have to just focus on L to get this transition, but what will be the energy of EK and EL, that we have to keep in mind. So now if you draw it, just we are focusing on K and L. One electron is still there, one electron is kicked out and one electron is coming from L to K. So now K orbit is very close to the nucleus, right. So we can think like this, the overall Z atomic number should be Z minus 1, because there is one negative charge. This electron, we can think this electron actually in the nucleus. This is actually approximation, we have to think, because otherwise we can't do that, na, because there is a we in Bohr's model we are just accounting the nucleus, charge of nucleus, we are not accounting the other electrons, but here there are other electrons as well. So we have to take care that. So we can think that as K orbit is very closer to the nucleus, so we can think that the one electron of the K orbit, other one electron, that is actually in the nucleus. That's a very naive approximation, we can say, but we have to do that, otherwise we can't apply the Bohr's model. Okay. So now the electron is Z minus 1, okay, in the nucleus. So En should be minus 13.6 Z minus 1 square divided by N square, obviously in electron volt. So this is very important. So in this way we are accounting the role of other electrons. Okay. So now if this is the case, then what will be the Ek? For Ek, N is 1, so it will be 13.6 Z minus 1 square. What will be the El? Minus 13.6 Z minus 1 square divided by 4. So what will be the del K? Oh, sorry, not del K, del E. Del E should be El minus Ek. So it is actually minus 13.6 . Okay. So this is, so if you calculate it, then we can figure it out that del E is actually equals to 10.2 Z minus 1 square. So this is the transition energy, and due to that transition photon of X-ray is released. So what will be the energy of that photon? H nu, or we can write it H K alpha nu. That's the case, but we are writing the nu, H nu. So it should be equals to the nu, or you can write nu is 10.2 by H Z minus 1 square. Okay. So root nu should be root over 10.2 by H Z minus 1. So if you plot it, what will be the plot? This is, so 10.1 by H, we can write it as C Z minus C. So this is the equation. So now we can plot it. This is root nu and this is actually the Z. Then we can obtain, so it should be like, there is a negative intersection, so it should be like this. So we can obtain the straight line. So using the Bohr's theory, we can explain the Moseley's result, which is actually del nu proportional to Z. This is explained. So that's why the Bohr's model is so amazing. It can explain the experimental result, though there is ad hoc approximation, but still we can able to explain. So this is the Moseley's total law and the experiment. But let me stop here in this part. In next part, we will discuss the importance of the Moseley's law, and we will conclude this class and this total chapter by giving some summary. Okay. So let me stop here. We will meet in the next part again.